Located 93 million miles away, the radiation emitted by the sun 8 minutes ago is only just now hitting the Earth. Even after energy dissipation, about 44 quadrillion watts of power fall upon our planet every year. The sun is a massive opportunity for energy generation waiting to be harnessed, and Collegiate Solar Partners aims to do just that. Solar power is most often associated with photovoltaics, but there is another much lesser known type of solar energy generation called concentrated solar power, or CSP. Even the most advanced photovoltaic systems are limited to a conversion efficiency of 23%, while CSP can achieve efficiencies exceeding 40%. CSP technology uses motorized mirrors called heliostats to track the sun and reflect its radiation to a tower located at their core. On this tower, the area receiving radiation, called the receiver, gets extremely hot. It contains a falling heat transfer medium, or HTM, which absorbs the reflected solar radiation. Depending on the residence time in the receiver and the heat capacity of this medium, it can store thermal energy for hours after the sun has set. The heated HTM is sent through a heat exchanger to generate steam and power an electricity-generating turbine. First and second generation CSP technologies used molten salt as their HTM, but faced issues with structure corrosion and oxidation as the salt undergoes thermal degradation. In response, the Generation 3 particle pilot plant was created by Sandia National Lab, proposing an HTM that utilizes conductive solid particles, such as sand or bauxite fracking propants, instead of molten salt. However, the efficiency of solid particles as an HTM is heavily affected by the uneven temperature distribution throughout the bulk of the medium. This is caused by a non-uniform curtain of particle flow, where particles block each other from receiving thermal radiation by the heliostats. To address this, Collegiate Solar Partners developed a prototype that promotes uniform particle fall by adjusting key parameters like particle agglomeration and delivery position. The design features innovative hopper and grate designs at the receiver to optimize spacing and reduce the effects of air entrainment. The prototype consists of base brackets for the extruded aluminum support bars, a vinyl tube as the receiver body, a locking ring to secure the grate assembly, and finally a 3D printed hopper and grates sized for the particle mesh. Grate testing showed that 2mm holes best minimized agglomeration at the inlet, and drawing from mineral processing techniques, square holes outperformed circular holes when transferring irregularly shaped particles. Of those tested, it was determined that a sinusoid with square holes worked best for maintaining a well-distributed particle curtain. Prototype success was evaluated through visual analysis of curtain uniformity and instrumentation, utilizing a potentiometer, laser, and analog light sensor to measure light absorption of the particle curtain across different grate designs. Within the year, integration of the prototype with a solar simulator is scheduled to determine its commercial scale viability, advancing the path towards clean, innovative solar energy.